my name is Georgi Radulov, and in this video we'll consider the concentration distribution of minority access carriers in PN junctions. So here I give you a PN junction. This is a diode which is in forward biased mode. Very quickly about the forward bias mode, we connect this external energy source VA, the positive potential to the P side and the negative to the N side, so that it creates an externally applied field in this direction which opposes to the built-in electric field, so that the resulting electric field is reduced electric field, internal electric field from the N to the P side. Because we reduce the electric field inside the PN junction, the potential barrier that exists between the P side and the N side, which is visible by the bending of the band diagram, this bending is reduced by the amount of the externally applied voltage. This means that now much more electrons will have the needed energy to overcome the potential barrier and eventually diffuse to the other side. Here in this picture the carrier concentration is given. Here we have the electrons which have the sufficient energy to diffuse to the other side, and they appear at this side. Their concentration at this point can be expressed with this formula, which is the normal level in thermal equilibrium, the concentration of electrons in the P side at thermal equilibrium, which is this level, times an exponential function of the externally applied voltage VA and the thermal voltage. So what you can see is that at the edge of the space charge region, the concentration of electrons, which are minority carriers in the P side, jumped here exponentially. So we have a change in magnitudes of their concentrations. The same happens with the holes, of course, from the P side injected to the N side, where the holes are minority carriers. Their concentration jumped from their normal thermal equilibrium concentrations. They jumped this concentration at the edge of the space charge exponentially with the same function, exponent of VA divided by VT. So now the question is, what will happen with these high concentrations? What will happen with the concentration of minority carriers in injected excess minority carriers in the P or in the N side? So first of all, what we can observe is that there is a big gradient, a big difference between the concentrations of minority carriers at the edge of the space charge region and deep in the semiconductor. So why is that? First, when the electrons exit the space charge region, they are now in the P side of the semiconductor, in which they are minority. And the majority of the carriers there are holes. So they are now in an area with abundance of holes, a lot of holes. So the chances that an electron meets a hole are very high. And we know when an electron meets a hole that they recombine and annihilate each other. So what we will have for sure is recombination between holes, majority holes, and minority electrons. So the concentration of electrons will drop. The other thing that will happen is that the high concentration of excess electrons injected in the P side material will reduce due to diffusion. So there is a one point where we inject the electrons and they're in an area with low concentration of electrons, so they will diffuse from this side. So there are two mechanisms that reduce the concentration. The first one is recombination, the second one is diffusion. So what we can expect is that the concentrations of electrons will drop eventually to the thermal equilibrium levels somewhere far deep in the semiconductor. And then there will be a function in space defined in which according to which the concentrations will drop. By the way, the same happens with the holes. So here are the holes, and their concentration will actually drop. So what exactly is this spatial function? What is this function that governs the decrease of the concentration of minority carriers? We can investigate it through the ambipolar transport equation. The whole form of it in one dimension. We have the diffusion term. This term is due to drift. This is the generation term. This is the recombination term, and this is the dynamic term accounting for the changes. We consider now a special case, and in this special case we can simplify very much the ambipolar transport equation. The first thing is that we will consider steady state, and steady state means that there are no dynamics. So we connect a DC voltage source from the outside, and it settles to a certain steady state condition for which a constant amount of charge is continually injected from one side to the other side, which actually constitutes the DC current. But here the point is that in steady state there will be no dynamic, there will be no differences in the excess charge injected. So the excess charge, the amount of charge that we inject, is constant, yeah? And this is actually this value. But this allows us to put this term to 0. There will be recombination, because as the electrons come here and then they see a lot of holes, they will recombine with the holes. So this term is important. There will be no generation, so we ignore the generation term, and we can assume that the electric field inside the N region or the P region is 0. Then for the holes, so basically if we look at this side of the holes, we have the second derivative term, which is the diffusion term, and we have the recombination term. We rearrange the constants, so we have two constants here. One is the diffusion constant and the other is the lifetime constant, and we can define the diffusion length constant. So in this case, L gives the almost average length that a carrier will travel whole before meeting an electron and recombining.
Now this is a simple linear second order differential equation, and you can just type it in Wolfram alpha, so of this type, and this is the solution. You get the solution. So the solution is basically given for the excess carriers, given with two constants, the constant A and the constant B. Now the challenge is to determine these constants A and B. We have two constants and we have two initial conditions, or boundary conditions. The first one is that at infinity, at the space infinity, all excess carriers will have already diffused or recombined. So there will be no excess carriers, and the minority carrier concentration will be at the levels of thermal equilibrium. So this means that this point here, eventually at x infinity, will be here. Yeah? So all excess carriers here will recombine and diffuse in this region. So if we have this initial condition, then we can find A, and so how we do this? So the excess carrier concentration of holes in the N material for x infinity is actually Pn0, so this will be here, this is the boundary condition, minus Pn0, so this is 0, and it's equal to A E plus infinity Lp plus B. Now e to the power of minus infinity is of course 0. So this is 0 and this is infinity. So the only solution that this is 0 is if A is equal to 0, and then we have one of the terms, A is equal to 0. So this can be ignored. Now we have the term B, the constant B, and then we use the other boundary condition, which means that at the border of the space charge region, the concentration is known, is this concentration. We derived it in the previous video. So then we write again the equation for the excess carriers at point xn. So the excess carriers at this point are of course Pn0 exponent Va divided by Vt minus Pn0, and are equal to B E minus Xn Lp. So from here we can derive the constant B to be Pn0 then E Va divided by Vt minus 1 E Xn Lp. And then the generic solution for the excess carriers, the function in space, will be simply this thing times this thing. So this will be Pn0 e to the power of Va divided by Vt minus 1 e to the power of Xn minus X divided by Lp. So this equation, if you plot it, it will be something like this exponential settling. The same thing, the same function can be found for the electrons injected in the P material. Again, such a function. Here we can see for Va positive, it will be like this, and it will be like this. So now, because of this gradient in the concentration, so this is carrier concentration, there will be a diffusion current in this side. And this current, so just propagate like this, and here diffusion current of holes, so this is diffusion current of electrons, this is diffusion of holes, will propagate in this side. And this will actually constitute the current that is flowing through the PN junction. Now this is the carrier concentration for a negative Va, and for negative Va, of course, the concentration at the edge of the space charge region will be 0. So this means that the solution of the function will be something like this. Like this. And now the diffusion current is in the opposite direction. So it will be negative current, but what we see is that the current will eventually saturate because the concentration here are 0, so they cannot go under 0. Now we can plot the current. At thermal equilibrium, of course, we don't have current, so this is this point. And for positive Va, we saw that we have some sort of an exponential function, which is governed by this function. As the injected excess carriers are increasing exponentially with Va, the current will be increasing exponentially. Then here, the exponential function will continue in negative, but then it will eventually settle to a constant value, which is the negative reverse bias exponential current. And it settles to a constant value because the concentrations cannot fall under 0. So they will saturate, so the current will saturate to this value, and this is only the diffusion current of the minority carriers of thermal equilibrium, all of them migrating to the other side. So thank you very much for your attention.